spectrum, an immense scale we use to measure the wavelengths of all kinds of radiation. At one end are radio waves with the longest wavelengths. At the other end are gamma rays with the shortest. In between are the other bands, including visible light, which is such a tiny fraction of the whole, it's difficult to imagine. How small is the visible spectrum? If you had a reel of movie film representing the entire electromagnetic spectrum, stretching 2,500 miles from California to Alaska, the section containing the visible spectrum would fall somewhere in the middle, near the University of Washington.
Sorry.
This frame is the whole visible spectrum. It is one frame and over 2,000 miles of tape, and it's everything that the human eye can see. The importance of this frame is that stars emit almost all of their light in this part of the spectrum.
So guys, if you want to see more about that, I highly suggest looking at the links, but try to give you a visual for how small that visible piece is that we're going to be playing with. But what's tricky about electromagnetic wave is that you're dealing with an electric field oscillating, and you're also dealing with a magnetic field oscillating. If you think about it, when we were doing induction, if you have an electric field that's changing, you get a magnetic field off of it. Well, that magnetic field, as it changes, it induces a current. And so if you think of these two waves, they're perpendicular to each other, and they're constantly driving each other forward. And so as they oscillate, they're using each other to propagate. It rhymes. Highly suggest finding a way to understand and remember what the electromagnetic spectrum is. On one end, we have radio waves, huge, long wavelengths. Infrareds, a little shorter, we get into visible. If you notice, infrared is on the red end, and ultraviolet is on the violet end. And then we get into X-rays, and then we get into gamma rays. The idea that I think I would like you to remember is the stuff down here, this is the stuff that is the most deadly to you. This is the stuff that has the most energy associated with it. It's the stuff that will basically react and cause cancerous mutations. So, the ultraviolet, X-rays, and gamma, they're all things that will hurt you. Infrared, whatever, radio, you're fine. Right in here, though, we have our microwaves. And what makes microwaves tricky is that they have the frequency that resonates water. And so that's what makes a microwave powerful, is that we can put things into a microwave, heat them up by oscillating just the water molecules. The things that I think I want you to remember is the speed of light is big, 3 times 10 to the 8th. And this is not just light, this is all electromagnetic waves. All of them. The letter we use for it is C. Well, C equals F lambda. That comes from V equals F lambda. So nothing different there. Visible light happens between 400 and 700 nanometers. Red is on the long end. It has the big wavelength. Violet has the smaller wavelength. As frequencies increase here, the wavelengths decrease. And so these have very short, very small wavelengths. These radio waves have very big wavelengths. Next thing, light travels. When we say light, I want to emphasize this. We're talking about electromagnetic waves. Travel in a straight line until they reach a boundary. When they hit a boundary, well, things change a little bit. When they hit a boundary, there's two things that happen. One is that some of the things reflect. If I were to think of this as like a mirror, all of it would reflect. If it was water, some of it would reflect. If it was glass, a certain portion of it reflects. It all depends on what the material is. But the angle of incidence, which is the angle it comes in at, equals the angle of reflection. Next up, refraction. Refraction is, if this is my surface here, like this is glass or water, as it enters it, it bends. Tomorrow we will come up with a way to think about which way it bends and why. But for right now, in your notes, the angle of incidence, we'll call that theta 1 here. The angle of refraction is theta 2. And so this we're going to use, and this angle is measured off of, we refer to this as the perpendicular. And so sometimes you'll see it listed as the angle from the perpendicular to the surface. Next up, n is what we refer to as our index of refraction. And the index of refraction, well, the thing is when light enters these different substances, it slows down. Once it leaves the substances, it speeds back up. But as it enters it, it slows down. And this index tells us how much it slows down. So the index of refraction is the speed of light, c. So the c is the speed of light divided by the actual velocity. The key is as light enters a medium, the speed changes. What is the speed of light in ice? Well, the index of refraction of ice is 1.309. So the index is c divided by b. So 1.309 is the index. Speed of light is 3 times 10 to the 8th divided by its velocity. Solve for its velocity. That's it. Ivan Sol, if I said his name wrong, forgive me. Baghdad, 984, came up with the idea of mathematically describing how much light is bent. Willibrord Snellius, great keeper name, he came along and basically said the exact same thing, but he used a little more algebra. Then René Descartes comes along and he does the same thing, basically stealing Snellius's theorem, the French refer to it as the law of Descartes, forgive me. And but what do we call it in physics class? Snell's Law. Not fair, is it? He came up with it. He ripped it off the guy who ripped it off of him, and we give the credit to this guy. Genius. You noticing a little bit of bias? Yeah, it's all about going back to Ivan Sol. He's the guy who did it. So Snell's Law. Two things are in Snell's Law. One is that the frequency of light does not change. That's idea one. So if I think about light coming in here, it bends, but the frequency out here and the frequency out here are the same. It has the speed of light out here and it has a slower speed inside. The one thing that's constant is this frequency. This is Snell's Law. This is algebraically, n is the index out here, the theta is the angle, the other theta is the theta inside that it bends to, and I have the index on the inside. Notice the direction that this bends. It should have gone in a straight line, but it bends towards the normal. Let's do one problem, and we'll get you out of here. Beam of incidence is the angle you come in with. The angle of refraction is 23.4. Find the index of refraction for the slab. The big idea is if I come from air, the index of air is 1. So I have n sine theta equals n sine theta. Air, the angle that it has of incidence, going into the slab, we don't know what its index of refraction is, and it gets bent to 23.4 degrees. Solve that out, and I solve for n. 1.45. Frequency. Well, if I want to find frequency, V equals F lambda. And the V outside is 3 times 10 to the 8th. And so my lambda is 651 times 10 to the negative 9 nano. Here's a practice problem. This is the more classic question you'll ever get. A beam of light is incident at 23 degrees. So it comes in and it is incident at 23 degrees and it gets bent. The index in here is 1.52. The index out here is 1. What is the angle between the refracted and reflected ray? This is what we refer to as the refracted, and this is what we refer to right here as the reflected. And this reflected happens at the same angle, and this angle we need to solve for. An angle. And so the question's asking you what is the angle between them. You're solving for this angle right here. All right, thanks for tuning in. Have a good one.